Hi guys, welcome back. So this is going to be the second video in our series on antibiotics. This is the follow-up now to our first video, which was on the structure of bacterial cell walls and how peptidoglycan's made. That video is really important for understanding this particular class of antibiotics, the beta-lactams. So if you haven't watched that video, or you couldn't get your head around it just quite yet, I'd really highly recommend watching that video before watching this one. Otherwise, you might not understand a few of the words that I'm going to be throwing around. And it's really important to understand peptidoglycan before we understand how to inhibit it. Okay, so getting right into it. This is the beta-lactams are a massive class and probably one of the most famous classes. They gave rise to our first ever antibiotics. This class called the penicillins, which I'm sure you're all familiar with. So things like Penicillin G and V, they were Penicillin G in particular was what was discovered to be growing in a petri dish produced by a fungus, and it was noted that with this fungus, when that grew in the petri dish, there were no bacteria growing around it. They did a lot of work, isolated the compounds, realized those compounds that the fungus was secreting was what eventually became penicillin G, then was modified to give penicillin V, and so on and so forth. As we started to understand how these drugs worked, we could then start using different kinds of molecular modifications to give us all these other different structures, which all act in the same way. They just have various side chains and things added to them in order to increase the efficacy against a certain class of bacteria. So looking at this list, there might be a few names that you recognize. Methicillin for one, if you've heard of MRSA, Methicillin-Resistant Staph Aureus. We'll cover that in a little while. Amoxicillin is very commonly prescribed. Cefotoxin as well. There's quite a few. Cefalexin is also very common. Ampicillin, very common. Anyway, you guys can read over that in your own time, but just to show, it's a massive class. There are even more available than these. And just to give you an idea of some of the structures here, this is what a few of the structures look like. Now, you might be able to see that there's a few different kind of characteristics that each of these seem to have, and the most basic unit is this kind of structure here. You can see that all of these compounds have this structure in them. And this is what's actually the functional kind of unit, I guess. So all these bits out here, these are all just and the R group as well. They're the bits that we modify in order to give us all the different types of beta-lactams. But this thing here, this is what we call the Beta-Lactam Ring. This is kind of enlarged. This is the most important thing. So this is the lactam ring, or the beta-lactam ring. Beta-lactam ring. So this is the important thing. This is actually what makes penicillins work. The way that penicillins work is, if you remember from the previous video, I mentioned transpeptidases, those penicillin binding proteins. So they're named penicillin binding proteins because they were actually discovered through studying penicillin. When we were trying to figure out how penicillin worked, we realized it was binding these proteins, or better name to call them penicillin binding proteins. So the transpeptidase, you can see here, is what we said that was responsible. Actually, if I scroll up, we said that the transpeptidase was what was responsible for linking this glycine group between the D-aller and the L-lysine groups on separate blocks, separate building blocks. That's what the transpeptidase did, so that's why it was important in building the cell wall. We can see here, so this is the D-aller bond. So if I kind of draw it out here. So this is the D-aller bond. So if I go right up to the start again, remember, this was our original building block. We had these two D-allers at the end. This terminal D-aller is cleaved and then combined to a pentaglycine in order to make a strong linkage. So this is the bond that actually gets cleaved here. So the transpeptidase binds onto this in those building blocks, cleaves it, and then brings in that pentaglycine chain to make it nice and stable. You can see the similarity though between this and this our little binding block right here. So this is the R group, so this is one of the things that can be modified, so we're going to ignore that for now. We're going to ignore all this as well. Really, the thing that we need to focus on is this bit here. And you can see how similar that is to this DL bond, this Beta-Lactam ring. So you've got the nitrogen connected to a carbonyl group coming up to this R group, which, you know, can vary. And then really the only thing that differs here is that the beta-lactam has got an extra carbon in here, forming that kind of arrangement. That's the only thing that differs, right? So what happens is if a bacteria is susceptible to penicillin, its transpeptidase, instead of binding this DL bond, it comes in and it binds to this penicillin beta-lactam ring. And whereas when the transpeptidase binds the DL bond, it can cleave it quite easily. With the beta-lactam ring, it binds to it and it binds irreversibly. And it can't cleave. It doesn't matter how much effort it tries in. It's almost like, the way I think about it is if the enzyme's like a jaw, and, you know, the DL bond is a marshmallow. It can chomp through that easily, but penicillin's the jawbreaker. It just keeps trying and trying and trying to chew it, but it can't break. It's very strong. And what that does is it irreversibly inhibits that enzyme, so that enzyme can't detach from the penicillin, and so that transpeptidase is lost. And if that transpeptidase is lost, then eventually you overwhelm it, you saturate all the transpeptidases that are in that cell wall. You can no longer cleave that bond, so you can't make any more peptidoglycan. Peptidoglycan, as with most things in the cell, it needs to be constantly turned over so that the cell doesn't die, because, you know, it gets modifications from being in the external environment with chemical reactions and things going on. So if you don't constantly replace it, then the cell, the wall will eventually deteriorate and the bacteria will die. That's the method of action of penicillin and beta-lactams in general. So they're a very powerful class. We class them as what we call a bactericidal. So what that means is we have two kind of classes of antibiotics and antibacterials. We have bactericidal. These directly kill bacteria, whereas bacteriostatics kind of stop bacterial growth. We'll touch on that in one of the later videos. But so penicillins and beta-lactams, very, very strong bactericidals. What they do is by binding to the wall, they induce defects in kind of a two-stage mechanism. And then the defects mean that the bacteria wants to fix, and so it starts actually degrading its own cell wall. But because it's got an inhibited transpeptidase, it can't make more peptidoglycan, so it ends up chewing up its peptidoglycan wall and then lysing, because it ends up killing itself. It can't withstand the osmotic pressure, because you have you've got this bacteria here. It's a nice thick bacterial peptidoglycan wall. You get the penicillin. You start erasing into this wall, and so and it's kind of like a renovation. The bacteria says, okay, well, we've got this defect here. The best thing we can do is just knock out the entire wall and we'll try and start again. So it does that and it eats away its wall. But when it does that, suddenly there's nothing stopping the cell from swelling. This is really concentrated in here and dilute the two solutions, so water flows into the cell. The cell swells and then it lyses and the bacteria is dead. So that's how those beta-lactams work. Few examples. So Penicillin G and V we talked about before. They've got very, very, very low toxicity. They're kind of like our go-tos. Unfortunately, there's a lot of resistance to them now, which I'll talk about in a sec. But if they do work, they're excellent. They've got such low toxicity. You can, if the person's not allergic, you can give basically as much penicillin as you want. They're not going to overdose. They're more likely to get sick by the sodium ion that's also kind of, so these penicillins kind of administered as a salt attached to some sodium ions. You're more likely to get sick from the sodium in the penicillin than you are from the penicillin itself. Very easily cleared by the kidneys, not toxic because it only acts on those transpeptidases and as none of our cells have transpeptidase, there's no kind of side effects or anything like that. Allergy is possible. That's probably the biggest thing that we need to kind of consider. And then going back to that the list that we had before, so like all of these have got different specificities for different bacteria. Ampicillin is a really good example of a nice broad spectrum antibiotic. And flucloxacillin, which I'm not sure if I can find on the list. Flucloxacillin is basically the clinical version of methicillin. We don't use methicillin anymore because it's very, very, very toxic. But from methicillin, we actually got a whole bunch of other antibiotics. The one that we use at the moment is flucloxacillin. It's the clinical equivalent of methicillin. And so when we talk about MRSA, which you may have heard about, the golden staph, so that's Methicillin-Resistant. Staphylococcus aureus, so I'm just going to say Staph aureus. So MRSA is actually what we're referring to is flucloxacillin. So we don't use methicillin in the clinic. What we're saying with MRSA is it's resistant to flucloxacillin, and often it's resistant to a lot of other antibiotics as well. Cool. So that kind of brings us nicely now into how we get resistance to penicillins. This is, again, one of these really important topics to kind of understand, because we need to understand how bacteria are overcoming our antibiotics so we can design smarter antibiotics which kind of evade these mechanisms. The first version, or the first way, I guess, that bacteria can overcome beta-lactams is by producing this enzyme called beta-lactamase. Basically what it is it's an enzyme that it's not involved in production of peptidoglycan, so it's not a transpeptidase, but it binds to penicillin specifically. It binds to that, not penicillin, the Beta-Lactam ring, in fact. So it binds specifically to that ring that we talked about. And unlike the transpeptidase, the beta-lactamase can cleave that ring and snap that right in half. And once the ring is cut, that penicillin's out of the game. So there's no way that it can, you can't come back or anything like that. It's now gone, out of use. So you can understand then, if you've kind of given someone a dose, say for example, and you've given them 100 beta-lactams per se, then the beta-lactamases are essentially just going to run through all of those beta-lactam rings and chop them all up before, and then those beta-lactams really get a chance to bind to the transpeptidases and have their effect. So they can be very, very potent. There's a bacteria you may have heard of called Pseudomonas aeruginosa. Pseudomonas, and then the last name's always really hard to spell. Pseudomonas aeruginosa. This bacteria is very, very resistant to a lot of things. It's very hard to kill. It's a common hospital-acquired infection, and very common in people who are immunocompromised, immunodeficient, so the elderly, people on chemotherapy, things like that. They have outbreaks of it in hospitals. It's very, very, very hard to kill. If you've ever noticed, so in the bath or the shower, you get kind of that green kind of slimy things inside bath toys and all that kind of thing. That's on usually a biofilm of Pseudomonas aeruginosa. It loves nice wet environments. It's got a greeny blue color. It's got a very distinctive smell as well. It's described as smelling mousy, which, probably doesn't make any sense until you've smelt it. But very, very, very hard to kill. How that relates to this is that one of the ways it has resistance is that it has intrinsic resistance to beta-lactams through making this beta-lactamase. So these cells, these bacteria, even before the introduction of penicillin back way back when it was discovered, these cells already were expressing this enzyme for a completely different reason that we don't know yet. And that granted them intrinsic resistance to beta-lactam. So these have never been susceptible to penicillin. There are two classes of beta-lactamase. So they can be encoded on plasmids, or they can be chromosomally encoded. So if we have our bacteria again, so you might know bacteria have a one really big long chromosome. So they don't have lots, they've got one big circular chromosome, but then they also have these little kind of floating packets of genetic material called plasmids. So these are almost like tiny chromosomes, and they independently replicate, independent of the cell, and they can be transferred as well between other bacteria and between the environment and the bacteria. So they're very interesting. So they often encode antibacterial resistance and things like that. So they're of real concern. Plasmids often encode them, or they can be encoded directly on the chromosome. Pseudomonas aeruginosa, as we said, is intrinsically resistant, and that has a chromosomally encoded beta-lactamase. Now, you might be wondering why I'm being so pedantic about this. The reason why this is important is because one of our main methods of overcoming resistance with beta-lactamase is this beta-lactam called clavulanic acid, or clavulanic acid. So what this is although it's a beta-lactam, so it's got that beta-lactam ring, it's classed as a penicillin actually, it binds to transpeptidases, but it binds them quite weakly. So it's not actually, by itself, it's quite a poor antibiotic. What it's really good for though is it binds to plasmid-encoded beta-lactamases very, very, very strongly. It binds them with a really high affinity. And so what that does is it's almost like a magnet again. So if we imagine that the beta-lactamase is, again, a jaw, and now our beta-lactamase can eat our jaw breakers really easily, because it's got, hydraulic jaws or something like that. When we give it the clavulanic acid, instead of going for the other beta-lactams that are being co-administered with the clavulanic acid, this is like a jawbreaker covered in, it's like a meat pie covered in tomato sauce or something like that. It's something really, really yummy that that the beta-lactamase wants to eat. So the beta-lactamase selectively binds to clavulanic acid, forms a really nice complex, and what that does is it allows the other beta-lactam that's been administered to go and bind to the transpeptidases and kill the cell. So if we say, let me see if I can draw this out. So say that this is our clavulanic acid, and we often administer it with another beta-lactam. So for example, you may have heard of amoxiclav, which is amoxicillin with clavulanic acid. So this is our amoxicillin. And we'll make that our transpeptidase. And last of all, this is our beta-lactamase. So when there's no clavulanic acid in the picture, our amoxicillin will be trying to bind to the transpeptidase, but our beta-lactamase is going to bind to it first, and it's going to form that complex, and it's going to break up the amoxicillin. Right? What happens though when we co-administer with clavulanic acid? The beta-lactamase starts heading towards the amoxicillin, but then sees the clavulanic acid and instead goes and binds to this. And it binds this really nice and tightly, and kind of munches on that, and it's happy. It's kept busy. And while it's distracted with the clavulanic acid, the amoxicillin is able to go in, come on, there we go, bind to our transpeptidase and inhibit the transpeptidase. And then you get cell lysis and things like that, as we mentioned before. So clavulanic acid, really important way to overcome plasmid-encoded beta-lactamase driven resistance, I guess. If it's chromosomally encoded, as it is in Pseudomonas aeruginosa, for other reasons, it can't bind clavulanic acid. So the beta-lactamase, the chromosomally encoded beta-lactamase does not bind clavulanic acid. It's not inhibited. So you can't give someone with Pseudomonas aeruginosa infection amoxiclav, because it's not going to do anything. Like basically the chromosomal encoded beta-lactamase is going to continue to destroy the amoxicillin, so there's no point giving it. Okay, still with me so far? We're nearly wrapping up now. The last thing though is the second method of resistance. This is probably going to be the biggest video in the entire antimicrobial series, by the way, so don't worry, they're not all going to be like this. The second class, so this was beta-lactamase. This is the altered PBPs, or I said I was going to call them transpeptidases. So what you can do is, instead of encoding something to break down the beta-lactam, you can just change the structure of the thing that the beta-lactam was going to bind. So whereas most transpeptidases might look like this, and this is our beta-lactam, they go and bind nicely, we just change, excuse me, we change the transpeptidase, we change the binding site. So now it can't bind to that circular penicillin anymore, that beta-lactam, because the binding site's changed. So now the beta-lactam does nothing. It's completely ineffective. There are a couple of bacteria that use this method of resistance. One of them is Streptococcus Pneumoniae. You may also know this as the pneumococcus. It's a really, really important pathogen. You get the vaccine for it as a kid if you live in Australia. It's really important. It's a major cause of otitis media, which is an inner ear infection. It's a major cause of pneumonia, obviously given its name, and also meningitis. So it's a really important pathogen. Before the vaccine caused a lot of deaths. And we used to be able to treat it with penicillin. We can't treat it with penicillin anymore though, because there's a lot of resistance due to these altered binding proteins. And so that's why now we need to be checking for resistance before we... So we might still use penicillin as an empirical therapy. However, we now want to double check that we're prescribing the right thing by doing susceptibility testings on culture. The second one, which I mentioned before, is that Methicillin-Resistant Staphylococcus Aureus. This has, so Staph aureus is very, very common in the population. Most people were colonized with it either on the skin or in the nose. So it's very common. Most of the time it's just a commensal on our microflora, but it can be a very potent opportunistic infection. So as soon as you get a cut or you become a little bit immunocompromised or something like that, or it gets into your bloodstream, it can be a very, very, very potent pathogen and cause a lot of illness, causes large abscesses, lots of pus, all those kinds of things. It encodes resistance. So this specific, the Methicillin-Resistant, it has the penicillin binding protein variant 2A. That's encoded by a MEK-A gene. This is found on plasmids. So remember before I said that plasmids are a really important way of transferring resistance? This is why. So not only can they transmit beta-lactamases, it can also transmit different varieties of penicillin binding proteins which are resistant to binding the penicillin, which is why that name gets confusing, because you've now got a penicillin binding protein which doesn't bind penicillin. So that's why we're going to call them transpeptidases. So MEK-A is a pathogenicity island on plasmids. And as I said, this transpeptidase has very low affinity for beta-lactams. So now, again, they have resistance. One final thing before I finish up is that penicillin doesn't cross the blood-brain barrier very well. So if we've got someone that we suspect has meningitis, for example, with Streptococcus pneumoniae or any other kind of bacterial meningitis, we're going to treat them with a third generation cephalosporin, which is still a beta-lactam. Where are we? Right back up here. So our third generation beta-lactams usually are the ones that we'll use there, such as ceftriaxone. These just have been modified so they cross the blood-brain barrier very well. And if someone comes in really, really sick with bacterial meningitis, you don't have time to do a culture. You just need to treat them empirically. We'll often use a third generation cephalosporin. All right. Thanks for sticking with me for that, guys. I know it went for quite a long time. If you've got any feedback or any questions, please leave them in the comments below. But if not, thank you for watching.